Okay, starting the recording here, and then yeah. So I guess today I thought we would go over a couple of examples of actually like constructing a logic using LADL for language that isn't the monoid, which is the one that we've looked at so far, and that can get us closer to the assignment that Greg gave on Monday of constructing a logic for the lambda calculus. And yeah, we're going to look at everything sort of up to the modal logic, and then explain, what the modal logic operators are. But then I think wait for Greg's class on Monday to go over how we actually go from the rewrite rules to the modal logic operators. So. And then I'm hoping that after we do that quick review, then we can get back to some of the category theory stuff and understand the encoding the monoid into a Lawvere theory, which is useful when we're actually like looking at the math and the category theory behind how the LADL algorithm actually works. All right, cool. So are you seeing my screen now?
Yeah, I see.
Okay, so up here we have the language for the monoid, and this is, when for our language for a monoid, we can either have the identity element, or we can have one of our generator elements, or we can take two elements and have this binary operation between them to get another element. So when we are when we pull this down and create a logic out of this, what we do is first we choose our notion of collection that we're going to use in addition to our language to generate our logic. And our notion of collection, the only one that we've really looked at so far in class, is the set. So we'll just continue to view these things as sets. You can do lists and other things, but we haven't really explored those too far. But LADL works with multiple different ideas of collections. So first we can, so here we're defining a new language, which is our logical language, and our new language will map to a collection of terms, a collection of statements. So our language here, we say that true, the meaning of true is all of the statements in our language. And our meaning of a negation is all of the statements of our language minus some set that we're negating. Or actually, this should be minus the meaning of A. And then this should also be.
And how could we practically do this, from the set of all possible expressions in our language, we are removing only one. How can we do this?
So this is just using our idea of set. So for example, let's just take what is, so A here is just like a stand-in, just like, we use M and N up here, or we use P other places. This, not A by itself doesn't have any meaning, because A has to be another thing of the form that we are defining on the left-hand side here. Does that help? Both A and B do?
I'm thinking how we know what is the full set of our language. Is it a finite set, or?
No, it's all the set of expressions
no, it's
generated by the first grammar.
Yep.
All possible expressions in our language.
Yep.
Yeah.
Exactly.
Okay.
Yep.
What does the L
so right, we can.
Why do we write L of M?
So that's just to say the language, the set of all terms that's generated by these rules.
The language, got it. Okay.
Yeah, the language of the monoid is sort of what we're looking at here. But like I kind of keep that, yeah, this is sort of saying the language of this monoid.
Yeah, it's not specific to monoids, it's about grammars, right?
Right, but it's about grammars, but in this case our grammar is a monoid.
Right.
Yeah. So right, so this we can get false out of this, right? Because false out of the rules that we have so far, because false equals not true. So can anyone know what is the meaning of false going to be?
Just be the empty set.
Mm-hmm.
Right. Right. Meaning of equals empty set. All right, and then so then if we have two statements and we AND them together, we just get the intersection. And by De Morgan's, we can get the OR as well.
So I have a comment.
Yeah.
Since we're in the structure of the monoid, shouldn't the empty set be like empty? Just to be consistent with the monoid structure.
So when we're talking about the meaning of our formula here, we're not talking about monoids anymore. Now we're talking about sets, because we've chosen the set as our collection that is collecting these terms. Does that answer the question? Or am I?
Yeah, I'm okay with that. Thank you.
Okay. Okay, and so all of those logical statements so far we've just gotten from our collection type. And now from our language, we also get to sort of pick out statements. So we have, right, our E, our identity element, and we can say that, this just picks out all of the statements in our language that are equivalent to the identity element. And then we have, we can use our generators as well in our logical formula, our monoid generators, and this is saying that we'll, again, pick out all of the elements from from our language that are equivalent to the generator that we're talking about. And then we can also use this binary operator up here in our logical language. And what its meaning is going to be is that our M is going to decompose. So we're going to pick out all of the things in our language that decompose into two parts. We'll just call them M1 and M2 for now, and that they decompose into two parts, and that the first part is in our first set, in the set A, the set meaning of A, and the second part is in our second set meaning of B. So you can see that we really haven't done anything fancy on the right-hand sides here, that this right-hand side stuff just sort of is logically following from our language. So if that's the case, right, then we should have all the information that we need to write down the logical structure for something like the blue calculus. So I thought we'd just do that right now together, and we don't have to do all of these productions. We can just do a few of them. But starting off, we can just start off with the meaning of false. What should that be if we're using set again?
So wait, we've left the whole monoid thing behind now, right?
Yep, that's gone. Yep, we're doing this. So we're running LADL using this language of the blue calculus and sets again still as our as the thing that is going to generate our logic.
Any particular reason you chose false first instead of true?
Just to show a different example.
Okay. Empty set?
That's empty, yeah.
Yep. And then we can do A or B, right? Which is going to be what?
Meaning of A, union, meaning of B.
Meaning of a what?
Union.
Yeah.
Yep. And then we need our not as well. And so that's just going to be, yeah, what?
I guess we just need to do A at some point.
Yeah.
We need to do A at some point?
Well, right, if we've done A or B and we've done not A and stuff, don't we need to get A in there?
So A is basically just a placeholder for a statement that we've constructed in our language, right? So like up here, it's sort of the same as what we're doing up here when we're saying M and N are defined by, we never really define M or N.
Uh-huh. Okay. Yeah.
So we didn't give the grammar
It never appears on the right-hand side.
Yeah.
We didn't give the grammar for the logic language, but there sort of is one.
Right.
It's the same structure, except that it has the ors and ands and nots.
Exactly. Right. It's yeah, but it's all of the things. The grammar is sort of embedded into everything that's on the left-hand side here, right? So you could imagine this being like here. So it's like A comma B equals false, or A or B, or not A, kind of like that. Does that make sense, Joshi?
Yeah, I'm wrapping my head around it. I think I'll see how this plays out, I guess, and maybe ask a better question.
Okay. So not A is going to be.
Sorry, may I ask one more question?
Yeah, go for it,
So
please.
is this A like extend? I can't say that word right. Extend, like for all A in this language. Is that what we're saying?
Yeah.
Okay. It's
this
not a
is
specific A. It's for all expressions in this language. That's what we're saying here.
Yeah, A is just so when we're putting this not A on this side, what we're really doing is we're saying that, okay, we have this idea of A and B, and these are our logical statements. And the way that we can construct those logical statements are in the rules that are sort of on the inside of the things on this left-hand side. So false is a logical statement. A or B is a statement in our logical language. Not A is a statement in our logical language. But of course, you need to start from something, right? So you can't just like, just like when you're constructing your process terms, you can't just write P and have it be a valid process, right? You need to build up from the zero process. So similarly here with all the rules that we've generated here, you need to build up from this terminal false.
That answered my question. That helped me.
Cool. But the other terminals that we get are actually the same things as the terminals in our target language, which we'll see in a bit once we move on to talking about this set stuff and the stuff that arises from our language. So not A is just going to be our whole language minus A again. And then now we get to add in
meaning of A.
Yeah, meaning of A, thanks. So now we get to add in, so what is our next rule going to look like? What's another thing that we can do in our logical language?
Well, if you pick one of the productions above, I guess X, I'm not really...
Sure. So we'll just call this like big X to differentiate, or we can just still call it X, I guess. And then what would the meaning of X be?
I don't have a good feel for that.
Singleton set with X.
Yeah. And so Pretty much. We're gonna define that a little bit differently because we're gonna take into account that things might be structurally equivalent. There might be two x's that are structurally equivalent, and like we're not looking at our we want to be like a level abstraction above structural equivalence when we're defining this. So we're gonna say we're gonna pick all the m's in our set L of m such that m is structurally equivalent to, I'll just use double equals for that. M is structurally equivalent to x. So that's how we'll write that.
And we skipped over the definition of structurally equivalent.
Yeah, that's not in there. There would be a definition of structural equivalence somewhere. So
Most likely alpha equivalence.
yeah, but for exactly, alpha equivalence will be included in structural equivalence.
Oh, and then there might be associativity with the bar and stuff. Okay.
Exactly. Yeah. Which, when we do, yeah. Okay, so what is another one of these going to be?
Since we did or, can we do and?
Yeah. Since we have not and or, we do actually already have and, right?
Yeah, we can just define it in terms of not and or.
Yeah.
So the meaning of A and B is the meaning of
Not A or not B.
Yeah.
Right.
This is the meaning.
Not open parenthesis, not A or not B.
Yeah. So what else do we need?
And in that and thing, you can take all the meaning things off. You can just say A and B means this and never mind.
That's true.
In other words, and is just a macro.
Yep.
So, I guess P of X is the next thing.
Yep.
Again, don't know, have a good feel for what that is.
Right. So the idea is we don't need to know what it is. If we can generate it, all we need to know is like the language generation rule. So the meaning of this one, can someone get me started?
So are we basically going to do the same thing as we did with X and just take everything structurally equivalent to whatever P of X is?
Yeah, almost. So note
Okay.
that P and X are both like terms in our language. So what we're going to say is that the M's that we have to pick are the M's that that decompose
Right.
into X here. So such that
So do we want to say decompose into like M1, M2, where M1?
right. Yep.
Okay.
Yeah. So this should be M1, M2 here,
Right.
and
okay.
then we're M1 in.
Meaning of P.
Yep.
Yeah.
I don't know why I have it. I shouldn't put that. Where M1 in meaning of P.
Yeah.
M2 in meaning of X.
And M1 and M2 are existentially quantified? There exist M1 and M2?
Yeah. Yep.
I can just read it that way.
Mm-hmm. Yeah, I'm trying to figure out where I should put that.
Well, after the first bar, yeah, you can say
This,
existing
right.
one, yeah.
Yep.
And the last line you want M2, yeah.
Yeah, thanks. Okay, is this starting to click? Do you see how we could go down the row here and say that all of these require two things now? So we would all say that, you know, we have something that decomposes. We'd have a rule that looks almost exactly like this rule.
Definitely.
Cool.
Yeah.
Yeah, I also definitely get that from a symbols manipulation point. I'm not sure I get the meaning behind it though. Like, are we running ladle right now? Is this sort of what ladle is, or like what do we achieve by coming up with all these equations?
Yeah, so let's move on to some of the next examples.
But to answer your question, there's nothing more than symbol manipulation, I think.
Right. The
Kind of
idea
important.
that. Mm-hmm.
Is it kind of like saying there are defined sequences of steps that we could
Yeah, an algorithm called ladle. That's what I'm getting.
Yeah. So yeah, there's symbol manipulation, just a defined sequence of steps, no sort of like human input needed to go from a grammar to a logic across that grammar. So
okay, that's starting to make some sense.
Mm-hmm. So now let's imagine that we have one of these things for the row calculus or row lang. Let's write some logical statements that mean my process sends data on X. Any idea how we would do that? What that logical statement would look like?
X bang, and then, I don't know, underscore or something. I don't know what to put there.
Underscore isn't one of the things that we can generate, but do we care what's being sent on X?
No? P?
So we could say that maybe the set of all programs.
Oh, okay.
And then, are we done?
Yeah.
So this will match X bang P. Will this match X bang P or Q?
Oh, no, it won't. I guess you want par true?
Yep. So now this statement here is a type. That means we send something on X. How are we feeling about that?
You lost me when you said it's a type. Can you expand on that? What do you mean?
Well, logical formula it can also be seen as a type, right?
It's the Curry-Howard thing, right?
Yeah, okay, got it, thank you.
Is this term in our language, logical language? Or
This term is in our logical language.
So in what we're doing, formula and types are interchangeable, right?
Yep.
Mm-hmm. Yeah.
But
Because this is... Yeah?
X is not a part of our logical language.
It is. Right, just like up here, right, we're saying that, oh, right, yeah, so I think you might be bumping up against something that is confusing me a little bit too, because I don't necessarily know how you define these things when, so like in pi calculus and row lang, just a mention of X, just like a mention of a name isn't a thing in your grammar itself, isn't a term. So there's probably some sort of manipulation that you have to do that some trick in the algorithm that I'm not aware of that gets you from your
In other words, names are not processes. Processes
right.
are the top level thing.
Right.
So what if we said that, yeah, I guess sends on X, you could put an @ sign in the bottom there.
Yeah. I think yeah, that's true.
And it's really sends on @ X.
Yeah. I think for these examples, let's just the idea being that any single program statement that you can make in your program language is a logical statement as well. And it's a logical statement that will only match things that are structurally equivalent to that program, given the output of the LADL algorithm.
So that top one we wrote right there, that means where we did X bang true, par true, that means like certainly sends data on X, right? Is there a way to express like may send data on X, you know, and it kind of depends what else. So I'm thinking like if we have some COM event, then the continuation sends data on X, but that COM may never happen because of indeterminacy or something like that.
Yeah, so that is, in the logical language that we've described so far, we don't have the ability to do that. That's why we need to add the modal logic.
Don't we, if we put the first part as an AND that may evaluate to true or false, then it may or may not evaluate the second part of the part?
Well, what would the first part be? What do you?
So if you put a proposition in the first part,
What
or
proposition?
something that evaluates to true or false, don't we have that already?
No, not that I'm aware of.
I mean, so are you saying something like this?
Yes.
So that's just equivalent to saying
True.
true.
That's everything.
Well, not quite what I'm saying. I'm saying having something that evaluates to either true or false.
So, Kevin, can you give us a little, maybe tell us a full example?
Yeah, so instead of true, if you put A, and A may evaluate to true or false. And then or, what we have, X bang, whatever.
Yeah, well, A is not actually in the language. It's just in the grammar.
Oh, I see. I'm getting ahead of that. Okay, thank you. I'm getting ahead of myself.
Well, that was a good question to help me.
Okay, so then how would we do something like does not send data on X?
Well, negate the thing above, so just put not around the thing above.
Yeah, that's right. That's not what I'm using for negation. Okay, and then maybe we'll just not do receives data from X or Y. We can see how you do that. But let's try one sends data only on X. How would we do that?
Just X being true.
Okay, that's
That's only sends data on X.
We need something else too, right? Because we're not saying we're saying that we could receive something as well. So we would want X bang P or 4Y from X Q. We would want that to match as well.
Well, some hand waving around P and Q there because they're grammar symbols.
Yeah. Yes.
Just 4 like true into X. true?
Yeah, so if for and x were our only, if send and receive were our only two things in our language, that would probably work. Just have something that matches all the fours. The nice thing about our logical formula, though, is that we can say, let's talk for a second about all the things that don't send on x.
So do we need to say something like doesn't send on not X?
Right. So this would be send on not x, right? And then I think we need that there too.
And then do we need a top level par true?
Wait a minute. Not. Oh, sorry. Par was true. Okay.
Right, because this right here is everything that's sending on any. So just like we have this up here means sends data on X. This down here means sending data on anything but X. The highlighted part. And then we can negate that to get the set of all terms that don't send on X.
Anything but, don't send on anything but X.
Yeah, right.
What if your formula?
Sorry, go.
What if your formula has multiple sends on X?
That's fine. They all match the first part.
Okay.
This does involve some tilting the head to the side, doesn't it?
Yeah. No, another send on X can still be inside of this, right?
Well, how do you mean? Only in the true part, which is negated.
So this is the collection of all terms in our language that. Yeah, I don't know, Christian. That's a good question.
So the example you're pondering is like if I do X bang 1 par X bang 2 because it's 2 sends on X, that's what we're considering?
Yeah. Does that match this formula? So the question is, yeah, that should match, right? Because we can say either X bang 1 or X bang 2 is going to match this part. And then for this part, anything that, any term that isn't sending on a collection of names that aren't X are going to be included. So a send on X can be included in here.
Yeah.
Wait, the X bang 2 does not match the right-hand side, right?
It does.
It does.
Well, it doesn't match the send on not X, right?
That's right. X bang 2 fails to match with send on not X. But since we then have that negation out front of there, send 2 on X matches with the entire right-hand side.
I see. Okay.
Yep.
But we're still happy, right? We've still solved the
Yeah.
assignment. Okay.
Okay. So the modal logic. This is is going to allow us to answer statements like can never send data on X. And this is going to involve our reduction rules and everything. And this will give us the new operators in our logic, possibly and necessarily X, which also follow some similar to Morgan's rules, meaning that like not possibly X means necessarily not X. So how would we write can never send data on X then?
Everything that X reduces to, sorry, can never send data on X. Well, oh, okay. So we're just sort of assuming we've run LADL with the reduction rules and all that kind of stuff.
Yep. And what that's going to give us at the end of the day is being able to have add these modal logic operators.
Can never send data on X means, well, is it necessary?
Never means necessarily, and then a not, and then however we're going to say send data on X, I think.
Yeah, how do we say that?
We did that up above, I guess, right? X bang true. Oh, yeah, right.
Yeah. Cool.
Yeah, this is pretty cool.
Yeah. So with that, unless there are any other questions or comments, I'd like to turn it over to Daniel.
Why didn't we do receives data from Y or Z?
Just for time.
Okay.
Yeah. But you could see how you have, you have you have this form is going to be receives data, and so you'll have two of these with an or between them, right, for our logical formula.
This feels a little bit like learning regular expressions and trying to get them to match. Does anyone else think, are those related or something?
Yeah, distantly, yeah. I mean, it's discrete math.
Well, okay.
Yeah, sure. I mean, you're talking about, you're using a language to talk about a collection of terms, and you're doing the same thing here.
Cool. I guess I'll start then. So let me just figure out how to share my screen. There it is.
It should be at the bottom middle.
Yeah, I see it, but I'm not seeing the option of the my PDF.
The window you want to share? Yeah, sometimes that
It's
gets a little annoying.
things.
You might have to,
what do I have to do to get?
you might have to restart Zoom.
Oh, really?
Yeah.
Okay. So let me leave, and I'll be back in a sec.
In the meantime, Dan was asking Jake if do you put those text files in the repo still?
Yeah, I've been lazy about that, but yeah, theoretically they should get uploaded to the repo, and then also theoretically I should go back and clean these up and put some text around them to make sense outside of the discussion.
Well, sharing it as is, I would really appreciate it if you did. Any cleanup is above and beyond the call of duty as far as I'm concerned.
Okay, yeah. I'll throw it
Yeah,
in
it's not recognizing in the option
Weird.
my PDF.
Can you close and reopen the PDF?
Oh, yeah, let me do that.
That's nice.
Let me just close all these PDFs I got going here.
Sometimes if you have it open in like a web browser or something, it'll just have the name of the web browser, and then...
Oh, no, it wasn't in a web browser. It was in my viewer. Okay, now let's try it. Now, did I lose you guys?
Nope, we're here.
But where the heck? I don't see anyone. I can't. This is so confusing. Oh, okay. No, it's still not appearing. Huh. Maybe I'm just going to close out Zoom entirely and
Okay.
see what happens. Huh.
There we go.
Yeah, that's not my thing.
Oh no.
That's my browser, and that's not what I want to share.
Can you open the PDF in your browser?
I guess I'd have to email it to myself, or I could.
You probably can like click and drag the file.
I could just go to Dropbox. I guess I have it there. All right. Fine. Okay. There we go. Let's see if I can hit this. All right. So now we just gotta get to where we left off. All right, so I think we left off, I was basically talking about the monoid now. So I was going to define a monoid in the classical sense, and then show how it gets to, how you can encode it using a Lawvere theory. Okay, so here's a monoid. I'm not sure if we covered this last time, but I'll just go over this quick. So a monoid in the classical sense is a set, which I'll call X. And inside that set, there's some identity element. And there's also this binary operation on the set. So that means you can take two elements of your set and it returns a single one. And we usually call that multiplication. And then there's these properties that has to be satisfied. Namely that if you multiply on any element on the left or the right by your identity element, it's like doing nothing at all. You just get back your element. And also you have this associativity. So you can, if you're multiplying three things, you can either multiply the right two or the left two, and you should get the same exact element. So that's the monoid, but we want to capture this using Lawvere theory. So we have to take all this information and somehow put it into the language of category theory, right? So remember a Lawvere theory, so it has a bunch of objects. And so the set, the set that would be our monoid set is going to turn into a generating object for our Lawvere theory. So the Lawvere theory is going to contain objects 1, x, x times x, x times x times x, and so on. How do we get the identity element? Well, that turns into an arrow. So the typical way of getting an element of something in category theory is, since we don't have, you can't look inside objects, so we have to do it using arrows. And so we can say that there's an arrow from 1 to x. So this is abstract. So 1 isn't a set containing a single element, but you can always use that intuition. So So we can think of 1 as a set containing a single element and x as a set. And so what an arrow does, at least a set function, it will send the singleton set to whatever element in X. So it's like choosing an element in X, essentially. So this is an abstraction of that idea. And also, the multiplication is going to turn it into some arrow. So because we have this object x times x in our Lawvere theory, we can talk about arrows from it. And the multiplication arrow will just be some arrow from x times x to x. Okay, so that gets... Oh, sorry.
So that middle line, there's one for every x. There's an arrow that goes from 1 to that x. Is that right? That's not like
so there's only one.
Oh, there is just one.
Right now. We're only dealing with like a single typed.
Okay. So there's only one. There's only one object in our category.
No. So there's only a single type x, but then that single type goes off and generates other things. So it generates like products, iterated products of itself.
Yeah. Okay.
And then the zerofold product is this object of 1. So, all right, so maybe there's a bit of a difference how we're using the term type. So don't think of each, all right, so I guess it depends on your perspective, but when you can think of x as a type, and sure, x times x would be a different type. But really we're thinking of like everything, but I guess a better way to think of x times x is a list or a tuple, a double of type x. So really what we do is just we're gonna have all these tuples of type x in this category. Does that make sense? Does that help answer your question?
So yeah, it helps me start to get what we have going on here. I don't quite understand the identity element turns into an arrow, but I think it'll come soon.
So each term in our language is going to be an arrow.
Yeah, so we only have arrows. So in the classical definition, I just said, oh, it's actually some, you see this first bullet up here, you see that there's an identity element inside of X. Well, in category theory, we're not allowed to talk about things sitting inside an object. So this becomes the way that we talk about elements of an object. Right, so it's kind of like an abstraction of the idea that if this 1 here is a single point and this x is a set, then a function just sends this single point to somewhere in X.
Okay.
So an arrow is essentially just picking out an element of X.
Okay.
Right. So that's what happens in the set world. But in the abstract world of category theory, this is just becomes an abstraction of this idea in the set world. So this becomes...
But I guess what I'm trying to say is like categories have objects and arrows, right?
Yeah.
So our category has several objects, x to the 0, x to the 1, x squared, x cubed. Is that correct?
Yes.
Okay. And so then we have this, so the identity element, is it x to the 0 or is it an arrow that goes from x to the 0 to some different x? That's what I'm stuck on. Is
it's the latter. Yeah, so so the identity element is an arrow from x to the 0 to x to the 1.
Okay. Oh, to x to the 1, specifically to x to the 1.
Yes.
Okay. Okay, I can understand what that fact means now, and then I'll see how we apply it. Thanks for taking that detour for me.
Sure. Okay, and then yeah, so there's multiplication. Okay, so now we also had these equations, right? So you can multiply on left or right by identity element and associativity. So equations in category theory turn into commuting diagrams. So this is basically, a commuting diagram is basically like saying, oh, two different, like if I look at this one, the fact that this left-hand triangle commutes says that if I compose these two arrows, that's the same as this arrow, right? So we can talk about two arrows being equal, or a composite of arrows being equal to another arrow. So we have this equation. We want to multiply an element of x, an arbitrary element of x, on the left by the identity element. And what we should get is just x again, little x. So that equation on the left-hand side is captured by this left-hand triangle. So what this upper arrow says is, so you can imagine, so these are two arrows that we're sort of multiplying together, so that the E is going to be an arrow from 1 to x, and this ID, which stands for identity, which says do nothing, is an arrow from x to this x, and we're just sort of glomming them together. So on the left-hand side of this product, we're just picking out the identity element, right? So we're going from 1 to x. And then on this side, we're doing nothing. So we're sending every quote-unquote element of x to itself, right? So we're kind of like loading this product up with the identity element sitting in the left-hand slot and just an arbitrary element of x sitting in the right-hand slot, right? So then what we're going to do with that is multiply. So we're going to multiply the identity element times an arbitrary element here. So that's what we land on here, a multiplication of an identity, of the identity element times an arbitrary element. But then this arrow, so this kind of says, this is the equality arrow. This is also identity, because, I mean, just like in grade school, 1 times anything, 1 times any number is that number, right? So that happens here. 1 times an object is still that object. So this arrow, I didn't label it, but this arrow just means identity, like, so do nothing. So just send an arbitrary element to itself.
Did any of these arrows already exist from us just being a Lawvere theory, like that hypotenuse arrow? Did that already exist, or did we just create that by?
So that is automatically a part of our Lawvere theory, just because Lawvere theory is a category, and category has to satisfy certain axioms.
Yep. Cool.
Yeah. So this is just a plain old identity arrow that comes for free, and we actually can't get rid of it. So all in all, what this says is just sending an element of here to itself is the same thing as multiplying it on the left by the identity. Right, so that's what this commuting triangle says. And this commuting triangle says the same thing, except multiplying on the right by the identity instead of the left. Okay. So any questions on this one before we do the next one?
Yeah, I have one. In the top left corner of the triangle, it says 1 times x, right?
Yeah.
Is that the same? Would it be identical if I had written like x to the 0 times x to the 1st?
That would be the same exact thing, yeah.
Okay, cool. And so then if I follow that horizontal arrow, doesn't that say that it's the same as x to the 1st times x to the 1st?
So that's the domain, the codomain of, yeah, this is x to the 1st times x to the 1st.
Okay, cool. So it is in fact the case that, wait, the arrows don't mean equal to though, right?
No.
Okay,
no.
okay, got it. Yeah, I'm with you.
But, so yeah, this is definitely not equal to this. This is just like a process, a process going from this to this.
Roger that, okay.
Yeah, and this process picks out the identity element in the first big X and does nothing on the second big X. Okay.
Yeah, got it.
Okay. Cool. And then the second one, or the second diagram, expresses associativity. So if we, so what this diagram says is if we start here at the upper left and go to the right then down, that's a composite arrow. And that composite arrow is equal to the arrow if we go straight down and then to the right. Right. So it's like one hand. So this one arrow is like the, let's see, the left-hand side of the equation, and this composite arrow going down and to the right is like the left-hand side of this equation. And then equal sign says that these two arrows are equal. So I guess we could break down this arrow. So this is going from x cubed to x squared. And what it does is this m is taking these first two instances of x and multiplying them down and shoving that into this left-hand instance of x here. And then this ID here is just sending this third instance of x in the upper left, doing nothing, just sending it identically over to the right-hand instance of x here. So it's like we're multiplying so if this contains triples of things in x, then we're multiplying the first two and doing nothing to the second or to the third. Right, and shoving that into here.
I was just going to say, for clarification, that ID is not the same as our like identity element in our monoid. This is the identity arrow that comes with our.
Yes, yes. So the identity element I'm denoting with E.
Yep.
And yeah, the identity arrow always comes for free in every category. Every single object has an associated identity arrow, which is like do nothing. Yeah. So after we multiply the left two and then stick that into the first x here, now we can take that result and multiply them. All right, so that's kind of like the right-hand side of this equation where we multiply the left two, x and y, and then in the next step, multiply z. And then the other path around this diagram says, all right, so let's go from x cubed down to x squared, where instead of multiplying the left two, we're actually going to multiply the right two things and stick that into the right x here. And then this leftmost x, we're going to just send down identically. So now we're going to take that result and then multiply it over here. So this composite arrow is like multiplying the left two things first, the y and the z, and then multiplying it by x. And those strings should be equal. Right, so that's how we capture associativity in the Lawvere theory. So we're actually we're building out the Lawvere theory right now. So we're saying, in defining it, we're saying that these are diagrams that definitely exist in the Lawvere theory. Why do they exist? Because, well, we're sticking these arrows in here, this E and this M. Right? This E and this M need not exist in a Lawvere theory. But I'm trying to define a Lawvere theory for a monoid. And so I'm going to stick these in here because I want them. And then, once I have those, I can talk about like equations that they satisfy or that I want them to satisfy. So that's why these are diagrams that need not exist in any Lawvere theory, but I'm sticking them in to our Lawvere theory for a monoid because they capture these equations that a monoid has to satisfy. Right, so I'm choosing to put them in here.
Yeah, thanks. That makes a good amount of sense.
Cool. Okay, so if we kind of break it all down, a Lawvere theory for a monoid is a category. So its objects are this one, which is like x to the 0, x, x squared, x cubed, and so on. So the arrows are all of those projection arrows. I don't know if you guys remember those projection arrows, but once you have products, you have projections where you can, if you have like a tuple, you can project like any, whichever one in that list down to itself. So you can kind of like forget everything except for a single slot of your tuple. So that's like the projection arrows. Plus these arrows that I'm sticking in. So the projection arrows come for free because a Lawvere theory has to have products. And if you have products, you have to have projection arrows. And these arrows are not for free. This E and this M, I'm choosing to stick in there. And plus you also have all the compositions of the projection arrows with these, and you can take products of arrows. Where products of arrows is kind of like we did up here, where you can think of it like doing things in parallel almost. So that's the Lawvere theory for a monoid. We also have these equations between arrows in our Lawvere theory. And also, these are going to generate additional commuting diagrams, additional equations. Right? Kind of like if you imagine, if you take an equation, let's say, this left-hand side, E times X equals X. Well, now I can like multiply on the right, on both sides of this equation by another element, Y, and the equation still holds. Right, so like E times X times Y is equal to X times Y. Even though I didn't put that in there explicitly, it sort of follows naturally from this generating equation. So in a similar way, these diagrams will generate additional diagrams that commute in our Lawvere theory. Okay, so that is really, so it's all very abstract, but that's not actually a monoid. So it's more just a blueprint for a monoid. Right, so the nice thing is we had the definition for a monoid earlier, but then that definition isn't like a mathematical object, right? So it's just like some It's a concept that I'm communicating with someone. But now using Lawvere theories, this thing I just defined is a definition of a monoid, but it's actually a mathematical object too. So we can study not just the monoids, but we can study definitions for monoids mathematically. So that's kind of the cool thing about Lawvere theories. But it's no good having a definition of something unless you can actually get instances of those things. And so to get instances of actual monoids, we use functors. So the idea is, I don't know, I didn't really talk too much about functors, but a functor, all right, is a thing that goes from a category to another category. So remember, a category, it has objects, it has arrows, it has other certain arrows could compose only if like they match up. If the domain of one is like one ends where the other one begins, then you can compose those. And every single object has an identity arrow associated to it. So a functor really is just a mapping between categories that preserve these things. So that's a very rough idea. So this is kind of maybe a little bit more clear. So if we start with two categories, I'll call it 1C, 1D. They each have their own objects and their own arrows. And we'll draw a functor like this, right, from C to D. And so that means for everything in C, for every object in C, a functor will return another object in D, and we denote it F of C. And then to every arrow in C, it'll return an arrow in D. And notice an arrow has to go from, if an arrow in C goes from little c to D, then the image of this arrow, after applying the functor to it, has to go from the image of little c to the image of little d. Oh, that's a typo here. That should be little d. Also, all composable arrows, their images can be composed. So that if I have this diagram, these two arrows that can be composed in C, then either what I can do is I can hit them each individually with F and then compose them in D using the composition in D, or I can compose them in C and hit the composites with my functor F. And either way, I should get the same arrow, right? Whether you compose them first and then hit it with the functor, or you hit each individually with the functor and then compose it. Okay. And also, every single identity arrow, this should be a little c here. So for every object in C, we have an identity arrow on it. That goes from C to actually little c, another typo. Well, that identity arrow, when we hit it with F, should also go to the identity arrow on F of C. So all identity arrows get sent to the corresponding identity arrows. Okay, so those are all requisites to be a functor. So functors can also have all kinds of properties, like finite product preserving, and this is the kind of functor that we want for Lawvere theories. So we talked about finite products. Not all categories have them, but the ones we're interested in do. And suppose that now we have, excuse me, the categories big C and big D actually do have the finite products. So that means, given any list of objects, C0 through Cn, in our category C, I can take their product, right? And that's another element or another object in big C. I can also take lists of objects in D and multiply them all together to get a new object in D. All right, so since our functor takes objects in C, objects in D, let's see what happens when we apply our functor to C0 through Cn and also to the product. Well, this will give us a new list of products, F of C0, F of C1, and so on, and also an image for the product, right? So since we can take products in D2, we can take a product of F of C0, F of C1, and so on, and getting this. So this is also an object in D. So if we have that taking the product of the images of each of these elements is the same thing as taking the product and then applying the functor, then we say that our functor is finite product preserving. right? So that's like saying we can either apply the functor first and then multiply everything together, or we can multiply everything together and then apply the functor, and we get the same thing. So when that happens, we say the functor is finite product preserving. Okay, so to actually get a monoid, so let's say we have a Lawvere theory for the monoid. I'll call it T for theory. So let's say that we define that above. So an actual monoid is just a finite product preserving functor from T into set. So kind of like when we were describing that, the logic earlier for the blue calculus, we talked about the semantics thing, or like, you know, the meaning brackets. And those all had values in set. So a lot of times when people are doing logic categorically, they'll say that that semantics functor or that semantics bracket is actually a functor from something into set. So what that means is for every object in T, we're going to return a set. All right, so let's see what happens. So in our Lawvere theory, we have this object 1, aka x to the 0. And since it's finite product preserving, it has to go to like what's called the terminal, or what's called the terminal object in set. So maybe I shouldn't have said that because it's something you don't need to worry about. But anyway, because of our setup, the x to the 0 or the 1 has to go to a singleton set. Right? So it's forced to by the product preservingness. So our generating object, which is called x, that's going to go to some image of x, which from now on I'm just going to call m. Right? So I'm just changing the denotation of it. And I'm going to say what that sort of means in a second. But for now, I'll just keep going and saying, all right, so x times x is going to have to go to n times m, where remember m is the image of x on the graph. And then x to the n is going to have to go to m to the n. All right, so this is all, sorry, it's like a second bullet and a third bullet are true because this functor is product preserving. And then this m, we sort of call the carrier set of the monoid. Namely, x here, it doesn't have any internal structure or anything. It doesn't have any elements, really. But once we map it over to a set, now it's a set. And so this set is going to be the set of elements that our monoid has. Okay, so we also have to deal with arrows, right? Because a functor is going to map arrows in our Lawvere theory into set functions. So it's going to take the identity arrow, right, this is an identity arrow, to some new arrow from the singleton to m. Remember, m is the carrier set for a monoid, and this is a singleton set. So this, as a set function, all this information is here is picking out an element in m. Right, so that's all it's doing. And it doesn't, we don't care what it is.
What's the relationship between like the carrier set and the like set of generating elements for the monoid?
So not every monoid is, well, here's the thing. There might be a slight difference in how we both understand the term generating. I'm not,
okay.
There might be, I'm not positive. So I think M would be like how you're using the term the language.
Yeah, probably. Yeah.
Because mathematically, because I think what you're doing is like, all right, we have some like atomic elements, and then we can multiply them all together, like, you know, put them all together. And then after you perform all the possible operations on them, you get the language.
Yes.
All right, so that's how you're thinking of it. The carrier set, I'm thinking of it as the language.
Okay.
Yeah.
Cool.
Because mathematically, not every monoid can be described first by having a generating set. That's only getting you like a small fraction of the number of monoids that exist.
Cool.
Mm-hmm. So yeah, so this is like the language of our monoid. And what this is doing is picking out a special term inside of here. Right? We don't care like what the term is, it's just some term. It will be special later when we say what it does, but right now it's just some term. All right, and so we also have this multiplication in our Lawvere theory. So our functor has to take that over to some, oops, this is another typo. This is supposed to just say M here, not F of M. So it's going to take us over to another map that goes from M times M to M. Right, so remember M is like the language of all of our monoid. So it's going to take two terms in our language and return a single term. So this is going to act as the multiplication for the monoid. And then just for fun, it doesn't, because there's all these other things that like once you just throw in the generating elements and all the operations and all these other things sort of pop into existence. Well, here's one of those things, just for example. So if we have this thing in our Lawvere theory, so we'll do M times M. So this is gonna we're multiplying two objects and multiplying two objects in parallel. So like this will go from x4, right? So this M will act on the left two factors of this, and the right M will operate on the right two factors of this. So it'll be, we'll take a 4 tuple, multiply the left.
Isaac, can you mute? I think you got an alarm going on in the background.
Sorry about that.
So from x4 to x2, that's this M cross M here. So it'll take the left two terms and the right two terms and multiply them each individually, returning 2 terms. And then after that, we can multiply those resulting terms and come down here. Right, so this is an arrow that exists inside of a Lawvere theory. Right, so it's built up out of M, which is our generating arrow. And then once you have products, you can also do stuff like this. So a functor will take this over to the operation of just multiplying 4 things in our monoid, like x times w times x times y times z for terms in our monoid, right? And then multiplying w times x first and simultaneously multiplying y times z, and then bringing that down to, in the first slot, whatever the result of w times x is, and then the second slot where the result of y times z is, and then multiplying those two together. Right? So if our monoid is just the real numbers, you're just multiplying 4 real numbers together. Okay. So a functor doesn't only take objects to objects and arrows to arrows, but it's also going to translate these equations. So I had all these equations up top that live in the Lawvere theory. Right, so this is an I had 1 times x in the Lawvere theory, and that's going to go to 1 times m. And I also had x times x in the Lawvere theory, so that's going to go to m times m. And I also had x in the Lawvere theory, so that's going to go to just m. So then the image of this left triangle under the functor is going to be f times e times the identity. So what this does is, this f times e is going to operate on this 1 to m, right? So this is picking out the identity element. So now that I actually have a language for my monoid, this is actually picking out a specific term here. There's an actual term that I can put my fingers on here. And then in the Lawvere theory, I had x to x identically, but functors take identities to identities. So now I'm going the language of my monoid to the language of my monoid identically. So what I'm basically doing is I'm starting with this, and then I'm loading up this m times m with the identity in the left slot and an arbitrary element or an arbitrary term in my language in the right slot. And then what I'm going to do is multiply those two together by going down. That's what this f of m is. This is the image of f. Sorry, the image of the multiplication in f is going to take us to actual multiplication in the language of our monoid. Right, so here what I'm doing is multiplying. Oh, sorry? Is there a question?
I think that might be just background noise.
Oh, okay. So basically what this is doing is I'm multiplying identity element times an arbitrary term in my monoid. So this direction, and then going straight down from 1 times m to m is just sending an arbitrary term in here to itself. Right, so the fact that this commutes, and it commutes because a functor will always take a commuting diagram to a commuting diagram. So the fact this commutes says that if we multiply on the left, an arbitrary element on the left, that's the same thing as just returning the arbitrary element, the same arbitrary element. And then this right-hand side says the same thing, except we're multiplying it by the identity element on the right instead of the left. Right.
So Daniel, so what you're saying is because this commuting diagram, because this diagram is coming from a commuting diagram, that this arrow FE in our monoid now has to take that one object to the identity in the monoid?
So the identity didn't exist in the monoid until this thing comes about.
I see what you're saying. Okay, so whatever the output of that map is, that is now the identity element in our monoid, basically.
Yes, exactly.
Okay.
So it's not like that existed a priori. This is the thing that actually creates the identity element.
Cool. Okay, that's really cool.
Okay, and then this down here is our associative law. So remember, this is the multiplication of the monoid, like the actual multiplication of the monoid terms. So here we're multiplying the two elements on the left and then doing nothing to the third. And now we're multiplying the two results. And then this side, we're multiplying the second and the third slot and doing nothing to the first. And then we're multiplying the result. So this just gets you associativity. Okay. And then, so really all the monoid is it's a product preserving functor from the Lawvere theory monoids into set. Into the category of set. And so the category of all the monoids and their homomorphisms, not in the homomorphism, this should say all monoids and the homomorphisms, is the same thing as this is notation for the functor category, which I don't really want to get into, but this is, you can create a category whose object is all of the functors from our Lawvere theory T to set. Well, it's not just any functors. I put this subscript here to denote that it's only the finite product preserving functors. And then there's arrows in there that are things called natural transformations, which I think would be, if you know that, that's great. If you don't, it's probably something for another time. But so we're basically moving up, saying, all right, so monoids now are not like these static things that just sit there. They're actually like, if you think of a functor as like a process kind of thing, we're now seeing monoid as more of like a process kind of thing. And so that's all I have.
Cool. Thank you.
Sure.
Yeah, thank you.
Could I ask another question, Daniel?
Yeah, definitely.
So you said that when we start talking about the Lawvere theory, we have these n-ary products, right? And we have projections from each of the n-ary products, right? And that works for n equals 0, n equals 1, n equals 2, all the way up.
Yeah.
So is there any kind of relationship between our arrow that we're forming out of the element E, which is taking the 0-ary product to X, and the multiplication arrow that we're creating, which is taking that binary expression to X?
Not, we're kind of saying what the relation is.
Okay.
Back when, so in the Lawvere theory, I'll make it back here.
Right, so just with those like coherence conditions, right?
Yeah, exactly. Like here, this is sort of giving us a relationship between how this E arrow and this N arrow interact.
Right, but it doesn't tell us much about well, I guess the projection, well, it's sort of a different projection that's happening with the 1 cross X to X, right? That's sort of like a canonical isomorphism or something.
This, yeah, exactly. This is a canonical isomorphism.
Okay.
So I am being like a little bit glib here, I guess, in that here I'm saying 1 cross x or 1 times x, and here I'm saying x.
Right.
And you know, in grade school when we learn multiplication, we learn that 1 times anything actually is equal to that thing.
Right.
Where in category theory, there's different levels of equality, and
yeah, this is like a tuple, right? It's like 1 comma x, and we're just like forgetting about the 1 basically.
Yeah, that's exactly what's happening. So I'm being a little bit glib in that.
Yeah.
In writing this, but yeah, what you're saying, you're identifying something that's happening.
Okay, cool.
So in a sense, 1 comma x or x comma 1 is not completely the same.
Right.
Well, it could be, but it doesn't have to be. I guess it's a kind of annoying answer. So there are, let me see how I put this. So there are things. So all right. So this isn't actually, if we're using our intuition about sets or types, whichever you prefer, then as a type or as a set, this thing here is technically different from this thing here. But there are categories where, remember, these aren't necessarily sets or types, they're just objects. So there are categories where we say that this product could be actually equal to, in the very real strict sense of equal. So in a Lawvere theory, these, I think, would be not necessarily the same. But there are these things called props, which is another similar thing to Lawvere theories. So I don't want to get into what those are, but in this example, this would actually be equal to this in the very strict sense of equality. But here it wouldn't be, you're right. It would be canonically isomorphic.
Thanks.
Mm-hmm. Any other questions?
So I guess question of like where to go next. So from understanding this and moving into like how we actually understand the LADL algorithm and the categories that are needed there. Right now we've sort of given how we generate a Lawvere theory for a monoid, and I guess we can see from that process how we might also generate a Lawvere theory for an arbitrary language that's given, constructed by the terms, kind of like the blue calculus that I showed there. But when we and from that we could probably actually still even talk about how that translates into like the logic. But then when we're going to add the modal logic in, we need a richer definition of category, because not only do we need to capture our terms, but we need to capture our rewrites between them.
Yeah, so
right?
That's why Mike and Greg are thinking about so-called graph-enriched Lawvere theories, which, all right, so an enriched category means that, all right, so when I talked about categories, I talked about between any two objects, there's a set of arrows between them. Mm-hmm. So in an enriched category, you're replacing that set of arrows with a different kind of mathematical object of arrows. Mm. So for instance, like a graph of arrows, or like, I would call it a graph. Computer scientists, I think, are more likely to call it like a multi-directed graph, or a direct multigraph, or something like that. So you can replace, or you can have a monoid of arrows, say. You don't only have to have sets of arrows, you can have other things of arrows too. So once arrows become, so I think you can, All right, so if you're thinking of the objects as sort of types, sorry, if you're thinking of the objects as types, then you can think of the arrows. This is just an interpretation that is helpful sometimes. You can think of the arrows as proofs, or as proofs, saying, oh, if we're given this type, then, and this type, then an arrow between these two types means like a witness here returns a witness here. But then if we had a graph of arrows, now we have a bunch of proofs, but also edges between these proofs. So these edges would sort of capture the idea of rewriting a proof. So this is kind of how they are, I believe, thinking of capturing these rewrites.
Yeah. So I think stated differently again, which correct me if I'm wrong, but you know, if the like x cross x and the 1 cross x are again types, the arrows between them are the actual terms that would satisfy those types. And then if we can put arrows sort of between arrows, because we can now have graphs instead of just sets of arrows, then we can actually talk about how we move from one term to another term in our language. Meaning like how one term is rewritten into another term in our language. Okay, yeah. But because of the Curry Howard isomorphism, right? You know, types and proofs. You know, proofs are programs, right, in the Curry Howard isomorphism. So that makes sense. But there's
that's the more I guess that's like I have this other project that I'm working on, homotopy type theory, and like that's more of the, I think I gave you the more homotopy type theory perspective.
Mm-hmm. Yeah, cool.
So as far as where to go next, I don't know if Christian I think has a better feel for LADL than I do. He's been working with it longer. So I don't know if he wants to start bringing LADL into the picture or not.
Yeah, Christian, do you feel like we have a good background that you could start kicking off next week?
I think so.
Moving on.
Yeah.
Cool. All right. That would be awesome. Okay. Well, yeah, I don't have anything else. So unless anyone else has questions or comments, I think we'll end it there. Thanks so much for presenting and for going half an hour over. I really appreciate this explanation, and this is really helping me. So yeah, thank you.
Great.
Of course. Yeah. Thanks.
Thank you.
Okay. Bye.
See you.
Bye bye.